We did the long wave approximation and we looked at what it means. Let me start here. So in a zonally varying basic state, we want to see what long wave approximation does. So that was our Doppler shifted frequency with this constant R given by this expression. In the frequency domain, we had for mixed Rossby gravity wave, the dispersion relation looked like this, which approximates to this one. And omega is written as minus kc over 2n plus 1, where c is our gravity wave speed or a Kelvin wave speed. So the phase speed, phase velocity and group velocity for a long wave, long Rossby wave, which is also long mixed Rossby gravity wave, was just minus c over 2n plus 1. And then for each n, you get the relation between the long Rossby wave and the Kelvin wave speed. And we had said long Rossby waves can be approximated as non-dispersive, and hence this relation with Kelvin wave is expected, right? What does that mean in this context of what we're talking about in terms of accumulation and impact of the background flow basic state, zonally varying basic state? Looking again at our zonal wave number frequency diagram, we had Kelvin wave n equals minus 1, and under long wave approximation we had long Rossby waves appearing non-dispersive this way, propagating westward. Omega over k is negative, and the regular Rossby waves have this behavior. So you can see that this solid red arrow is what a real Rossby wave would go through in a zonally varying basic state, as we saw before. It would get stretched and then head into smaller and smaller scales and reach near zero Doppler shifted group velocities and accumulate energy, whereas the mixed Rossby gravity waves completely disappear in the long wave approximation, and long Rossby waves propagate right through non-dispersively. So this is not that realistic, even though it's been used extensively. So the transformation shown in the figures we saw before, as the mode travel from 90 degree east to or 150 degree east into the negative stretching deformation area where du dx is negative, near 120 west in the eastern Pacific. However, such modification of Rossby waves apparent in both theory and modeling results is completely absent from the equatorial dynamics governed by long wave approximation. So the atmospheric dynamic systems based on long wave approximations, which are actually, the simplification is done to get insights into equatorial dynamics and also, of course, achieve computational efficiency, and it simplifies the eastern boundary reflection problem in the ocean where we have boundaries. But actually it turns out to lack generality and probably not as useful as one would hope. Okay. So impact of longitudinal displacement of waves in why am I back at this? Okay, so this is just to put in the context of 712 and 713. So we saw this before, where we had these trapping happening when you have Rossby waves without the long wave approximation, and for the mixed Rossby gravity waves. So again, when we derived, remember, we put dv dt equal to 0 in the governing equations to get to long wave approximation, and that eliminates mixed Rossby gravity waves and makes the long Rossby waves basically non-dispersive like Kelvin waves. But the point is that they are not as useful as one would hope from the simplification they provide. Moving on to the vertical trapping, accumulation, and lateral emanation. This is critical. Lateral emanation is critical because when you move heat sources like during an El Nino, the so-called teleconnections or the signals in rainfall or heat temperatures and so on produced far away from the tropical Pacific where El Nino happen through these kind of emanations from the origin of the wave forcing. Okay, remembering our diagram showing equivalent depth versus longitudinal wave number with vertical wave number and the vertical scales. We saw the group velocities for longitudinal and vertical directions. Remembering again, this is for n equal 1, this is in meter per second, this is in centimeter per second. So you have long waves and short waves, so you can see the transition from the westward group velocities to eastward, and here we have upward propagating waves, so the group velocity is downward. If you look at the other way, then you will have reverse direction. That's the relation we are looking at. Okay, so the influence of the basic state on the vertical group speed poses the question of whether transient modes will propagate vertically sufficiently rapidly to move out of the troposphere near the source region before they approach accumulation regions where du bar dx is less than 0. So we are now combining longitudinal variation of flow field with vertical propagation and see how the two are related, or whether these vertical group speeds remain within the troposphere as they propagate away from the source region. Okay, remember we released waves from different places and looked at the impact of longitudinal variations of the basic state. Now we are trying to look at the vertical propagation and vertical accumulation. Equation 7.2, it's apparent that if m changes, then hn will change because m was proportional to 1 over hn square root, being inversely proportional to m squared. So hn is proportional to m squared. Thus an alteration in m will alter the horizontal group velocity cgx because hn affects group velocity and horizontal structure of a mode through changes in hn. So there is a strong coupling between everything now, the basic state, the vertical propagation, longitudinal propagation, and so on. So we can now look at the impact of vertical variations of the longitudinal basic state u bar. So in this case u bar z is negative because the zonal velocity is decreasing, whereas here zonal velocity is increasing. So you are going here from westerly to easterly, whereas here you are going from easterly to westerly. In this case, the vertical wave number will increase with z because of this stretching, and the vertical group velocity will tend to 0, so there will be vertical trapping. So if you have decreasing vertical shear or negative vertical shear, you can have vertical trapping, and if you have positive vertical shear or increasing u bar with height, then m decreases with height, so you are going to again drive cgz to increase with z because you are going to make the wave longer in scale and there will be vertical propagation. Okay, you still have to decide what will happen at the top of the atmosphere. So looking at the impact of the zonally varying basic state, we can see that the accumulation zone of the mixed Rossby gravity waves and equatorial Rossby waves is in this range of u bar x less than 0. Okay, so in this case, if there is accumulation, which means k is increasing, waves are becoming shorter scale, so the longitudinal group velocity is going to 0 and the mode is longitudinally trapped. So if ux is 0, ux is greater than 0, you are in a westerly regime, then k will decrease, waves will become longer in scale and group velocity will increase. Okay, so here is the increasing group velocity for the equatorial, decreasing group velocity for the equatorial Rossby waves, and decreasing group velocities for mixed Rossby gravity waves, and you have feedback to UX itself. This is the energy density. I should be careful there. Okay, so amplitude of the wave. What is the red line? Blah blah blah. Yeah, they were just forward and backward accumulation. So this is the forward accumulation, this is the backward accumulation of the longitudinal. So you have the information on vertical trapping and zonal trapping in this case. You can look at this in this schematic here, the composites showing the generation of waves and emanation to higher latitudes. So you have vertical trapping happening here in the eastern Indian Ocean, and there is zonal trapping and vertical propagation with emanation to higher latitudes over basically Africa, just over Western Africa here, and in the Eastern Pacific west of the Americas here. So there are specific regions where vertical propagation and emanation to higher latitudes happens. Okay, so regions of longitudinal accumulations are also regions of latitudinal emanation to higher latitude, which means the wave energy being accumulated because of interactions with the mean flow is also being radiated out. That's always important to see what actually happens to the energy that accumulates because of these processes that we are talking about. That's what is the basis for the teleconnections, right? We talked about ENSO teleconnections, which we will come back to later on. ENSO is a moving heat source, essentially, which means it's going to generate waves, and there is a basic flow in terms of weakened trade winds and other changes over the Atlantic and Indian Ocean sector, changes in the Hadley cell, the shear, and so on. So there is the wave mean flow interactions with accumulation of energy and emanation to high latitudes, which can be an explanation for the teleconnections as well. The last bit of the chapter just looks at quasi-biennial oscillation as an example of the mean flow and wave interactions. So you have starting with this structure here, where you have phase velocity being positive in the westerly regime, and you have vertical shear with easterlies here. So you have decreasing U. So on this side, the phase propagation is positive here and negative here, and you have vertical propagation happening here. So you can see that the interaction momentum transfer from the waves to the mean flow is going to affect the mean flow. So you're seeing the changes here, which ends up changing the U bar itself. So now you have no barrier for phase propagation in the vertical here. So you have clear vertical propagation with altitude, whereas here you still have inhibited vertical propagation. So the next phase, continued energy transfer because of this, is going to give you again change in the mean flow. So it's not just the basic state altering the waves, but the momentum transfer from the waves altering the basic state and bringing you back to this way to completely reversing the shear. Now you're going from easterly to westerly. So U bar Z here is positive, it's negative here. So we talked about how M changes and group velocity changes in these cases. So quasi-biennial oscillation is basically something where the signal is propagating down from the stratosphere. It's got a clear phasing which can be easily observed over this 2-year time scale. Quasi-Biennial means approximately 2-year time scale, and these are the processes of wave mean flow interaction involved in the zonal and vertical direction. So this is an example of how the wave kinematics and the interactions with the basic flow are going to actually be useful for interpreting the actual dynamics in the full system. Okay, so we've been doing it as kinematics, simple flows, prototypes, longitudinal flows, and now adding vertical propagation and vertical variability of the basic state as well. And here we are showing an example of how interaction of the waves and the basic state is going to alter the basic state and the waves together. So that's kind of a good example of a feedback to produce this specific time scale of quasi-biennial oscillation.